Let me take a moment to introduce Doug. Again, it's my great pleasure to be able to do so. Doug Martinson is a Dougherty Senior Research Scientist in the Division of Ocean Climate Physics and an adjunct professor at the Department of Earth and Environmental Sciences of Columbia University. He's located at Lamont Dougherty Earth Observatory of Columbia University. Doug's research has focused on how changes in the polar regions feedback to drive changes elsewhere in the world. The goal is to provide proper assessment of the impact of polar changes on global climate and to predict the consequence of the polar changes on those extrapolar regions that are particularly sensitive to such change. Doug has spent a lot of his energy on ice flows and sea ice in the Southern Hemisphere, and his many wonderful, interesting, provocative stories about experiences he has had there. But I guess global warming will provide another type of dramatic experience. Thanks, Doug, thanks very much for coming.
Thanks, Dave. Ready for me to start?
Yep.
Okay, so I'm going to talk about the Antarctic sea ice and global warming, and including our inability to understand and model why the sea ice extent has been expanding until recently. But what I want to focus on, Claire showed all the data, I want to focus on some of the complexities of the ocean-ice interaction that may be very difficult to include because of their small scale in the global climate models or global circulation models, GCMs. And, but a lot of studies have been done, mostly by David, to test in the models, what's the impact of not being able to model these parts. But I first want to start at the comparisons. For a long time, people have been saying, hey, look, the Arctic's decreasing, the Antarctic's not, so global warming is not true, or the Antarctic's broken. Well, first of all, comparing the Arctic to the Antarctic's like comparing apples to army trucks. And the reason is the differences between these two regions are so dramatic, you couldn't even expect sea ice to echo that of the Arctic. Geographic setting, the Arctic, it's a landlocked ocean, limiting the maximum sea ice cover. Antarctic, continent surrounded by ocean, ice drifts to the warm waters, equatorward expansions limited by warm waters north of the polar front. Ice albedo feedback. Well, the Arctic, covered by a thick perennial sea ice cover, at least it used to be, all year round. In the summer, the loss of that sea ice in the summer opens up a really dark ocean, absorbing more heat and melting more ice, which enhances this feedback. The Antarctic, we're covered by a very thin, about 60 centimeter thick seasonal sea ice cover, which results in limited ice in the summer, so very limited ice albedo feedback. There's some feedback occurs where the ice is north of the polar circle, but that's always been going on. It's part of the annual cycle forever. Well, I don't know how forever, but and as far as ocean ice feedback, the Arctic, the stratification of the surface ocean prevents the deep ocean heat from affecting the ice growth. In the Antarctic, the stratification allows strong ocean ice feedback heat flux, which restricts the ice thickness to a thin, easy to remove shell. But despite these differences, we still can't explain why the Antarctic sea ice is expanding, though we're working on it. So here's Antarctic, and if you see all this ice here in the wintertime on the left, all this ice north of the polar circle disappears, so that's subjected to ice albedo feedback, but as I said, that's part of the annual cycle for forever, so nothing's changing with respect to that. And in the summer, we have these patches of perennial ice. Over here in the Bellingshaus in Amundsen, that almost all that perennial ice has disappeared. Now, it turns out the trends in the sea ice extent, they're not symmetrically distributed around Antarctica, and this is one of the problems for models. Typically, they haven't looked at that. It's like, hey, we get the expansion, or we're getting the change in the sea ice cover right, but they're not getting the distribution right. On this plot here, the Ross Sea down here and a Weddell Gyre, those are two areas where the ice covered days per year is expanding. Whereas in the Amundsen area over you can't see where I'm pointing, over here on the west Antarctic, a little bit over here, those places are decreasing. But when you average all the way around, we're having a slight increase until just recently, as Claire said. So let's look at some of the models now. The CMIP-5, that is there's a project. We're looking at climate model intercomparison project. This is the 5th edition of that. Here's a review of the results for the cryosphere by Shu et al. And what they show here is that as far as the seasonal cycle, the models are doing a superb job of catching the seasonal cycle of the Antarctic. It gets hot, it gets, don't tell me, cold in the winter and warm in the summer. Less ice in the summer, more in the, and they're right on there. The red are the simulations and the blue are the observations. But sort of a problem here is when you look at the trends, which Claire went over, I'm looking at a different period, so we get different slopes, but from 1979 or so to 2005, the simulations, the observations, as she showed, are increasing at about this rate up here, and the simulations are decreasing. Kind of a similar magnitude, just wrong sign. Some scientists can get away with, but engineers can't because they build the bridge upside down. Now, here's where they really fall apart. If you look at the monthly averages, the observations are all positive, simulations negative. That's bad. Same thing with seasonal. The models are all showing the ice decreasing, and the observations aren't. They're increasing. So, the Antarctic Ocean sea ice interaction demands very detailed modeling of small spatial scale processes in the surface ocean. This is something very difficult for large global climate models or global circulation models, GCMs, because they have to be able to run for years, not physical years, but they're simulating many years for the entire Earth. And they can't have tiny, tiny little scales, spatial scales in some places, though they are coming up with schemes now that they can do that. So there's some hope here. So let's look at the winter mixed layer system, how this is, how it works. So when the ice forms in the winter, what happens is the ice forms, the water freezes, and the brine, the salts and the minerals in the water get squeezed into pockets, and eventually they have their own thermodynamics and they melt through and release brine into the upper ocean. This brine is very dense. It makes the upper ocean denser, and as a consequence, the water has to mix down to an area where it's at a proper, so the water above is not heavier than the water below. Now in the Antarctic, we have this cold winter mixed layer, which is at the freezing point, and maybe 150 meters deep. And then we have a very sharp thermocline and halocline to the deep water, which is 3 to 4 degrees warmer than freezing. I mean, that is hot. What happens is when we're mixing into this thermocline, we're releasing heat. So we grow a unit of ice up here and release 1 to 16 units, enough heat to melt 1 to 16 units of ice. This is a negative feedback. It keeps the ice very, very thin, but it also keeps the ice very stable. If you warm up the system, this maintains about a 60 centimeter ice cover. And if you decrease the heat loss to the atmosphere, same thing happens. And this is one of the things David tested in the article that Claire was referencing in 1995. So now the thing about this system is it can be modeled with an analytical system, and the details of the system aren't important here. It's just the analytical solutions are very complicated. But fortunately for us, they're amenable to scaling laws, which are just arithmetic combinations of easy to observe variables. And these things capture the true analytical solution to better than 85% in the worst case. Most of the cases, it's better than 93%. So using these very simple combinations, algebraic combinations of easy to observe variables, we can actually capture a lot of these processes and not have to worry about the detailed scale model in a GCM. And one of the things we did was integrate the scaling laws so we get a more robust measure of the quantities and came up with some terms that make it even easier. For example, here, if you look at the freshwater content, what I'm calling the salt deficit, here's the amount of fresh water in the surface layer that has to be eliminated by brine rejection. That's the only source of salt. In order to you put this much salt in, and you'll have enough salt there to densify the whole surface that it'll convect to the bottom. But while you're convecting, you're releasing all this heat in a thermal point, which I'm calling a thermal barrier. And so what happens is, here we have, in this particular example, we have 7/10 of a meter worth of ice has to grow to eliminate this salt deficit. But while we're doing that, we're releasing enough heat to melt 3.6 meters. Now, what happens is the bulk stability of this is, if we're putting in this much ice here, 0.7 meters, so we're freshening the system by 3.6 meters. So we have to add those two together and say, and the sum, when rounded properly, is 4.4 meters. So we have to grow 4.4 meters of ice to overturn this system. Now, dynamically, this system, if you look at something like the Brute-Weisler frequency, which is a measure of the static stability of the water column, this water column here is equivalent to mid-depth waters in the Pacific Ocean, which most physical oceanographers would consider neutrally, no stratification. So one wonders, how does this not turn over every year? Because of this thermal barrier. So anyways, here's the feedback. Here's the ratio of how many units of ice would melt for every 1 unit of ice grown. And it varies from over to the eastern part of the Weddell, from 1 unit to 16 units. So you're saying, wait a minute, if I grow 1 unit, how can I melt 16? Well, here's how it's really working. Let's say it takes 1 day to grow a unit of sea ice. Now that releases enough heat to say melt 11 units. That means that heat, it'll take 11 days before that heat is vented to the atmosphere. So it's another 11 days before we can grow another unit of ice. So what it's doing is it's making the ice grow exceedingly inefficient. So we're growing ice, but super, super slowly, and hence that's why it's so thin down here. Okay, so now and as Claire said, I'm so happy to have been working with David and Claire all these years playing these games. It's great fun and very rewarding. But anyways, all sorts of numerous GCM tests of the climate sensitivity to the Antarctic sea ice distribution and thickness have been performed. And in particular, a series of studies by Rind and colleagues tested multiple aspects of this. This top one up here, where is it? The Rind et al. One. So we said, hey, look, it doesn't matter how you change the atmosphere, the ice thickness is not going to change much. So in Claire's thing where she said we don't calculate the sea ice calculation, that's the case here, where we said, okay, the ice is not going to really change thickness. So whereas most of the GCMs are melting all the Antarctic ice away because it's super easy to melt thin stuff, here we're keeping it fixed. And sure, as she said, in a 2 times CO2 simulation, that results in a 37% reduction in the warming. I mean, oh my God, that's a big deal because the sea ice isn't going away. And note here, the initial couple models in the CMIP2 runs with interactive sea ice, they do find this response for greater ice extent, but not so clearly for ice thickness. And then Claire led a project of the same group of us in 2001. And this one maybe is even more remarkable, a lot more discouraging as far as modeling goes. We're looking at the changes in sea ice concentration. And oh my God, if each year, if you misdiagnose 1% decrease in the sea ice concentration, that'll cause a global warming of 11 milledegrees. 1%. what are the odds of, I mean, how well we model the concentrations? Well, that kind of seems insurmountable. Thanks, Claire. So anyways, other rind showed the communication between tropical climate and the Antarctic polar gyres. And this is a great study here that brought together observations and modeling. And what he shows is when you have an El Nino, a tropical Pacific warming anomaly, when you have an El Nino, that intensifies the subtropical circulation, which moves the subtropical jet equatorward. That makes that available potential energy of cold Antarctic. It's moving the available potential of cold Antarctic continent in the Pacific, which leads to less cyclogenesis in the subpolar Pacific gyres. So we're spinning down the Pacific gyre. This tropical warming also perturbs the Walker circulation, which leads to the opposite effect in the Atlantic. So the decreased tropical Atlantic subsidence moves the subtropical jet, SJT, poleward. That spins up the Weddell gyre. By the way, the Weddell gyre, it's a cyclone, but everything's moving to the north, so that may expand the sea ice field. So the model explained, but the main thing here is the subpolar regional. It explains what we see. We see a spin down and a spin up according to if we have an El Nino or a La Nina. Here's one of the results from that Rind et al. 2001 paper. This is the mean intensity of storms. They're very mean. And here's a whole bunch of tests David ran. So here's a Pacific decrease. So we're doing the thermal gradient from equator to pole, and we're decreasing it. And all the dark areas are where the storminess increases. And here's a Pacific increase. If we increase on the right column, if we increase that thermal gradient, once again, we get these strong storms everywhere. If we decrease the Atlantic thermal gradient, storms everywhere in the entire Antarctic. If we increase it, same thing. And this goes through every single perturbation you can imagine. This is for the winter, the upper three panels. And if you increase the Atlantic gradient and decrease the Pacific, same thing. Everywhere in the Antarctic, you get increased storms. Opposite, same thing. And in summer, same thing. So the bottom line here is it doesn't matter which basin is having its thermal gradient modified, the entire Antarctic region is affected. All the Antarctic polar basins, not just the basin associated with the basin with the different thermal gradient. And this is a paper that Stammerjohn et al. Wrote that essentially shows the actual physics behind that. And I don't want to spend too much time going through, but when we have a positive southern Antarctic mode scenario, southern annular mode, we're getting warm winds and less sea ice here, upper panel, and cold winds and more sea ice there. And same thing with La Nina scenario, we get the same effect. So La Nina and positive SAM reinforce one another. And here's a study done by Lefebvre and Gouze that shows that the classical modes of atmospheric variability do not explain a large part of Antarctic winter sea ice extent. And so the Antarctic sea ice field does not behave as a single entity. So it's becoming kind of clear. You can't just say, okay, here's how much ice is around Antarctica. It's regionally different. So where are we now? Well, I know where I am, but clearly the model and observational studies show we do not yet understand why the Antarctic sea ice fields are expanding. But probably the most succinct summary of where we are was stated in a NASA press release following the Antarctic largest maximum sea ice extent ever recorded on September 19, 2014, was given, a press release was given by Claire Parkinson, the very Claire that just spoke. And I'm going to read it. There hasn't been one explanation yet that I'd say has become a consensus where our people say, we've nailed it. This is why it's happening. Claire said, our models are improving, but they're far from perfect. One by one, scientists are figuring out that particular variables are more important than we thought years ago. And one by one, those variables are getting incorporated into the models. And here's a key fundamental comment. It's really not surprising to people in the climate field that not every location on the face of Earth is acting as expected. It'd be amazing if everything did. So Claire said the Antarctic sea ice is one of those areas where things have not gone entirely as expected. So it's natural for our scientists to ask, okay, this isn't what we expected. Now, how can we explain it? Perfect, thanks, but great quote. And here's this, we're going to summarize here. So this presentation really focused on early studies attempting to determine the role Antarctic sea ice parameters, thickness, concentration, extent, play in simulations of global warming. Most of these early studies are by David Rind and colleagues. And some of the fundamental feedbacks, feedbacks that lead to an ability of the sea ice to self-regulate, i.e. the ice-driven ocean heat flux, and have a significant effect on the global temperature response to a doubling of CO2. And the results shown here, not allowing the ice to disappear, as was common in nearly all such model runs, the global warming was reduced by 37%. I mean, that is huge. And another one, errors in sea ice concentration as small as 1% can lead to global temperature changes of 11 millidegrees per reduction of a percent concentration. And finally, changes in the tropical polar SST gradients in a single ocean basin can influence conditions in all the polar basins, not just the perturbed basin. So the point of these things is not that they are absolute answers. Rather, these things are exposed on the sensitivities in sea ice conditions that are not fully addressed in most GCMs. So, questions?
Doug, thanks very much. I'm going to cheat here and ask you an extra textual question on a subject that you actually did not discuss today. But we were having a private conversation some weeks ago, and you sort of mentioned in an offhand remark that you can't see how the West Antarctic ice sheet can possibly be maintained as the climate warms. Did you want to make a comment on that offhand remark?
Okay, because we're all scientists, I can, but I hate saying this in public. The fact of the matter is, the global oceans, the deep waters of the global oceans have warmed tremendously. I mean, all that heat. So if we stop adding CO2 and take CO2 back to pre-industrial levels right now, we still have all that heat in the ocean, deep ocean. And there's one place on Earth right now where it comes out, and that's right in the West Antarctic. It comes out and it's melting the ice streams underneath, which they flow into the ocean, and then they jam up at the head of the bays, and that sort of acts as a bulwark to stop the ice streams from flowing. And once those things are melted from underneath, those ice streams speed up by a factor of 7. So they're increasing global sea level rise. And I don't see how we can avoid that. And of course, for long-term climate change, that's the biggest thing, sea level rise. So I don't want to, we still have to stop the warming, but there's a lot of CO2 and a lot of heat in the deep oceans. That's the point.
Okay, well, thank you for that optimistic point of view.
Yeah.
There don't see any questions in the chat window. So if there are no further questions, I want to thank everybody for joining us for this edition of the Lectures in Climate Change webinar series. Our next presentation will be in April. The date, I believe, is Tuesday, April 16th. It will again be from 4 to 6 p.m. I believe we have at least one speaker. We hope that you'll be able to join us then. And until then, please be sure to visit the CC Run website where you can view all of the webinars that have been previously recorded, and don't hesitate to contact if you have any questions for some of the speakers, and we'll get you in touch with them as needed. So thanks, everyone.
And Claire and Doug, thanks so much again.
Bye. Thanks, Dave. You're the hero here.
Yeah, Dave, thanks. And Doug, thank you. Wow, you were great.
Likewise, Claire. But